Good morning. My name is Brian Zerillo, and today our team will be presenting our submission for the RASC-AL Lunar Polar Rover theme, Explorer. Here is the team that designed Explorer. We are a group of senior aerospace engineers, all from the University of Maryland at College Park. Here you can see our agenda for the presentation today. First, we will cover mission and systems level information. Then we'll dive into the separate subgroups that make up our rover. In accordance with our RASC-AL theme, we designed a multi-purpose rover that can support robotic exploration of the lunar South Pole as well as expand a human crew's range by serving as unpressurized mobility. To meet the demands set by our theme, a number of mission requirements were created with direct relation to design needs outlined in the theme description. This includes support for high-priority science, technological demonstration, landing site investigation, and risk reduction. The rover will be reconfigurable for a 2-person, 6-day crewed mission and have the ability to operate autonomously and must cost less than $300 million and comprise less than 300 kilograms. Requirements were created for both the autonomous and crewed portions of the mission. Autonomous requirements include knowing position and pose, the collection of high-priority science data, and the ability to enter a safe mode in the event of a critical anomaly. The rover will also have sufficient power and communication capabilities for the operation in this phase, with the ability to have both uplink and downlink with Earth. Design requirements were set for a maximum velocity and slope in which the rover can traverse, as well as capabilities for driving over various sizes of obstacles. Systems level requirements for the 6-day human operation of the mission include the generation of sufficient power needed for EVA tasks, compliance with the NASA technical standards and handbooks on human integration, and maximum velocity, slope constraints, and obstacle clearance requirements during the crewed operation. Explorer will be constrained to a 14-kilometer range for missions away from the landing site, support a payload of 500 kilograms, and will operate for 6 hours every 24 hours during the crewed phase. The rover will be able to interface with the crew and provide information critical to human missions, such as the rover speed, orientation, and battery capacity. Here is an isometric view of Explorer, complete with solar panels, fenders, 2 chairs, a roll bar, and all of the other features that comprise the Explorer. Explorer will have an empty mass of 259 kilograms and a payload mass of 470 kilograms, allocated for the astronauts and their tools. This gives us a gross mass of 729 kilograms. The empty mass of 259 kilograms meets the requirement for a rover mass of 300 kilograms with a margin of 14%. The rover dimensions include a length of 4.7 millimeters, a width of 1.75 meters, and a height of 2 meters. The wheelbase is 3.7 meters, and the track is 1.45 meters. The power suite for Explorer includes a battery that will support 6 hours of crewed operation with 90% efficiency. It will operate at 108 volts and will provide 60 amp hours for operation. The battery will have 30 cells in series and will provide 6.5 kilowatt hours of energy and will have a mass of 48 kilograms. Explorer will have 2 solar panel support arms, each carrying a quarter circle panel with a surface area of 1.7 meters squared and an efficiency of 30%. The drive configuration includes 4-motor all-wheel drive with a maximum speed of 15 kilometers per hour. It will achieve 300 Newton-meters of torque at the wheel. The rover will consume between 35 and 56 watt-hours per kilometer and will operate for 20 hours in the autonomous mode and 6 hours in the crewed operation. Explorer will carry a suite of scientific instruments including 5 engineering cameras, a stereo camera, 2 spectrometers, a ground-penetrating radar, a magnetometer, and the Lunar Auxiliary Rover, or ALE, a small secondary rover for supporting high-priority science missions. The walk-back limit is the limit on how far an astronaut should travel away from the base to ensure their safety in case of rover failure. From a previous study, we assumed that the average velocity of astronauts was 5.6 kilometers per hour, the average velocity of the rover is 10 kilometers per hour, and the rover can operate for 6 hours. Assuming that the astronauts have approximately 2 hours to work inside the PSR, we have concluded that the walk-back criteria is approximately 14 kilometers. If instead the astronauts work inside the PSR for 3 hours, the walk-back range shortens to 11 kilometers. Since astronaut suits allow the astronauts to enter PSRs for up to 2 hours, the PSR has its own walkback criteria. With the same assumptions, the walkback criteria for the PSR is approximately 3.5 kilometers. The team found it necessary to determine the feasibility of a dual rover design for the Explorer because of the potential benefits. A cost analysis revealed that producing 2 smaller rovers could save as much as 20% in costs. Safety-wise, the dual rover could provide astronauts with an additional vehicle in the case of one of the rovers failed during a mission, and could potentially double their walkback range. We conducted a design iteration to determine the feasibility of this design. We assumed rovers would be nearly identical and that mass would determine dual rover feasibility. Here we have the mass breakdown for one rover configuration, and here we have the mass rover for the 2 rover configuration. As you can see from the mass breakdown, the dual rover design exceeds the mass requirement for the mission. Because of this, Explorer will have a single rover design. In order to have more data-driven decision-making when designing the mission strategy for our rover, we created a path planning algorithm that, on a large scale with a resolution of 10 square meters, would determine. In order to have a more data-driven decision-making when designing the mission strategy for our rover, we created a path planning algorithm that, on a large scale with a resolution of 10 square meters, would determine the optimal route between 2 locations on the lunar South Pole. The simulation achieves this by recreating the lunar South Pole environment in MATLAB using a set of contour color maps created from data collected by the LRO, with each map measuring a different environmental variable, such as slope or temperature. The contour maps are integrated into MATLAB as images, then scaled such that the colored data from the image now reflects the environmental data being collected. Pixels are converted to meters by scaling in accordance with the map's projection. Once the data set for the lunar environment is created, each position on the moon's surface is given a weight based on the impact that the environment at that position has on the rover's power supply. Then, Dijkstra's shortest path algorithm is implemented in order to find the optimal path based on environmental conditions. Seen on the left is a 2D map of the route between 2 points of interest, and on the right is a 3D representation of the same route. As can be seen, the rover cleverly avoids the ill-suited conditions of the Shackleton crater when traversing between 2 locations.
Hello, my name is Evan Kramer, and I will be speaking to the mission planning and analysis slides. The Explorer's mission is based on answering high-priority science and exploration questions. Assessing the local magnetic fields on the lunar South Pole will assure if sites are safe for human habitation. Defining the chemical composition of the lunar surface is vital to understanding geological history and identifying useful materials for crewed missions. Lastly, quantifying volatiles found in PSRs will also reveal information about early solar system history and what compounds are useful for human habitation. The science payload selected will collect data to address these questions. The engineering cameras will perform state of health checks, and the stereo camera will image the surrounding terrain. The spectroscopy systems will prospect for hydrogen concentrations in PSRs. The radar measures lunar regolith densities and will determine feasibility for crewed drilling. The Auxiliary Lunar Explorer, or ALE, will explore the deep regions of PSRs and collect samples. The magnetometer will measure the local magnetic fields. The CONOPS starts with Phase 1, the 1 year of autonomous operation starting in 2023. Explorer will land at the western rim of Shackleton and prospect it as a future landing site due to its near 100% insulation. Phase 2 involves supporting a 6-day crewed mission in 2024. Landing by the Sverdrup PSR allows for repetitive, non-arduous EVAs due to its low median slope. Phase 3 represents the end-of-life operation as Explorer autonomously travels to other PSRs of interest, taking surface measurements and creating topographic maps. To begin, Explorer will land on the South Polar Ridge near the rim of Shackleton. Initialization involves establishing two-way communication and calibrating the spectroscopy systems. Explorer will traverse to the far side rim of the Sverdrup crater in 1 lunar cycle, continually mapping the terrain and taking chemical composition measurements. Explorer will then conduct a series of PSR entries to map volatile distributions accessible during the crewed mission. Optimal routes to scientific sites will be planned. Lastly, the rover will remain outside the crewed landing ellipse before rendezvous with the lander. In Phase 2, Explorer will support a 6-day crewed mission. It includes 1 day of autonomous to crewed reconfiguration, 4 days of crewed EVAs, and 1 day of reconfiguration back to autonomous mode. The crew will enter and explore the Sverdrup PSR each of these 4 days. After each PSR entry, the crew will deploy a separately brought science experiment along the crater rim. Payload recommendations include a Langmuir probe, seismometer, and subsurface heat flow probe. No instrument deployment is scheduled for the final EVA to accommodate for schedule slippage or unplanned maintenance. During Phase 3 of its end-of-life operation, Explorer will travel to the eastern rim of Shackleton to deploy the ALE and then explore other nearby PSRs. The rover can support future missions through reconnaissance for landing sites and continue to scout locations for potential lunar habitat. The rover's batteries and solar panels may also be utilized as a power supply in future crewed missions. The ALE extends the science and exploration capabilities of Explorer. Its stereo camera will take images within PSRs, aiming to form a record of the solar system's origins. The sample caching system will allow for volatile extraction in the deepest parts of PSRs, where there is less reflected light inaccessible by astronauts. The ALE has a center section to house its instruments and 2 rotating sections with spikes powered by its motors. Its mass is roughly over 15 kilograms, requires approximately 200 watts continuously, and fits in a 0.44 meter cubed footprint. The ALE is tethered to Explorer in a similar fashion as shown in the top right picture, using the JPL Axel rover as a design point of departure. The tether will be a ½ kilometer in length, use a 3 millimeter diameter Kevlar K49 material, and have a mass of 5 kilograms. Original designs sought to directly power the ALE through a power cable within the tether. However, solely using a mechanical tether with an onboard rechargeable battery cuts mass by 80% and improved power distribution efficiency by 90%. To support 2 24-volt 120-watt drive motors, an onboard stereo camera, and a drill, a 15.5 amp-hour lithium-ion space-rated battery from Eagle Pitcher was chosen. This low-mass battery outputs 450 watts of power, giving a positive 155-watt power margin. The caching system features torque-driven, low-speed drilling to collect a sample of regolith from the lunar surface. The system was designed for minimal heat transfer by preventing sublimation to preserve the sample. The winch mechanism consists of a motor, gearbox, spool, and feed system. A high gearbox ratio allows the winch to be more efficient, allowing the system to have a mass of about 5 kilograms and fit onto the 40 by 50 centimeter mount on the back of Explorer. The feed system for the winch consists of a linear actuator and a circular guide. Wrapping the tether onto the spool in a parallel groove system distributes the stored stresses between layers and reduces the overall wear. Using the following costing model with the ALE's inert mass, the combined non-recurring and production cost totals to $26.7 million in 2020 dollars, once adjusted for inflation.
The structure of the rover was designed to directly support the requirements of the scientific mission and allow for safe crewed operation. After a trade study between various types of chassis, a space frame was selected as the optimal frame, and it was designed directly to support crew seating and the mounting of science instruments, as shown in this picture. The chassis itself is made of 1-inch steel tubing and weighs in at 16 kilograms. This design was preliminarily verified by a finite element analysis to show no yielding under basic loading scenarios and a simplistic crash scenario. The wheel was designed in concert with other domains of the rover using the Becker model of terramechanics. A woven wire mesh wheel was chosen over other wheel designs for its low mass and flight heritage from the Apollo rovers. The design stands 1 meter tall and 30 centimeters wide, with each wheel weighing 6.7 kilograms. This wheel is theoretically able to climb 30-degree slopes while crewed, even assuming a 20% slip in the soft lunar surface. To give Explorer full steering capabilities, each wheel is controlled by a linear actuator to provide perfect Ackermann steering. In the event of an actuator failure, the other wheels can work around this failure to ensure full turning stability. At low speeds, the rover can almost point turn, accounting for slippage. After a trade study of multiple suspension designs, a double wishbone suspension was chosen and a spring-damper combination chosen to attenuate the vibrations the crew will experience, to ensure a gentle ride in the low gravity. Also shown in this picture is the fender. It is a crucial component that attaches to the suspension on each wheel and provides a shield for the crew and components at the top of the rover to prevent the accumulation of lunar dust. One of the key features of Explorer is its reconfigurable nature. Because of this nature, the center of gravity is variable depending on its state. For example, the center of gravity is about 40 centimeters higher when the rover is crewed. This information is fed into the avionics system, where it automatically limits the possible turn of the wheels to ensure full stability of the vehicle during travel. This helps to prevent the possibility of forward and lateral rollover during normal operational circumstances.
Hi, my name is Matthew Phelan. I'll be presenting the crew systems slides. For Explorer, crew systems has focused on 3 major projects: adjustable and swivel seating, center console and lighting, lunar extravehicular visor assembly display, or LEVAD for short. Explorer is fitted with 2 side-by-side swiveling passenger seats separated by a center console, which supports the seats while they are in driving position and houses the crew-operated controller. With the center console in the middle, crew members are capable of operating the vehicle from both seats, allowing for both right-handed and left-handed drivers. Explorer's seats also feature a foldable and adjustable back seat, as well as loose fabric seating on the bottom and back of the chair. The adjustable back allows all possible crew members to operate the vehicle, while the loose fabric seating is designed to work much like a director's chair. It cradles the astronaut's legs in EVA backpack for a form fitting all around them, creating both side-to-side lateral stability and support while the rover is in motion. What's special about Explorer's seats is that they feature a swivel provided by a pair of twin tapered roller joints in the main support beam. The swiveling ability allows astronauts to have easy ingress and egress to and from the vehicle. No more jumping in and out of the rover like in the LRV. These seats move outside of the vehicle to accommodate for the moon's low gravity and the astronaut's prohibited dexterity. When the crew is ready to board, Explorer's swiveling seats allow crew members to rotate the seat, positioning outside the vehicle where it automatically locks into place. From here, the crew is able to adjust the backs of their seats in their desired height and depth using the extendable arms before boarding the Explorer safely while standing beside the rover. Once the astronaut is seated, the seat slides into a shelf in the center console for support. The T-bar is able to mitigate fatigue, allowing for astronauts to control it without the need to fully grasp it. They're able to cup their hands and rest it in the T-bar, giving them full control without having to suffer from the fatigue of fighting against the EVA suit to get a firm grasp on the controller. Cut position is a neutral position in the hand. This is combined with the wings and the ends of the T-bar. It allows the astronaut to maneuver in all directions with decreased fatigue. The T-bar is only a controller that has previously used in the environment for the same purpose. Design is simple and allows the astronaut to focus more on other tasks and have the ability to react more instinctively to their environment. There is less of a learning curve compared to other controller designs. This will allow for the astronaut to focus on keeping the Explorer stable. In considering lighting on the Explorer, 3 types of light sources were considered: LED, xenon, and halogen. After comparing efficiency and lifespan of these options, LEDs were determined to be the best option. The lighting system on the Explorer has the following requirements: 60 meters of visibility, use less than 30 watts, the ability to change lighting angle to support crew activities, and be capable of supporting cameras used for autonomous navigation, and last the duration of the mission. The lighting configuration consists of 2 LEDs mounted to the pole along with the cameras and sensors used for autonomous navigation. While the autonomous phase of the mission, the lights will be facing down and forward to eliminate the area directly in front of the Explorer for the stereo cameras. After the crew arrives, the lighting angle will be changed to illuminate the area further in front of the Explorer to aid the crew in driving. Lights are also capable of rotating to allow the crew to illuminate areas of interest in the areas they are working in. The Lunar Extravehicular Visor Assembly Display, or LEVAD, is a helmet-mounted display that is heavily based on another University of Maryland project called Visor. Unlike Visor, which houses a projector towards the upper rear of the astronaut's helmet, LEVAD attaches the projector housing directly above the astronaut's helmet. This allows for astronauts to easily attach and remove LEVAD at will. LEVAD provides an essential information relevant to the crew. This increases productivity and current awareness of the situation. LEVAD is able to connect the rover as well as the astronaut's spacesuit, providing a synchronized platform for information awareness. LEVAD works by using an off-the-shelf projector that projects through a diffuser mounted externally to the helmet, which then displays onto a piece of teleprompter glass. LEVAD has 3 different modes of operation that limit the information displayed to the specific actions, such as the lunar on-foot navigation mode, which displays a digital wayfinder to the direction and distance to explore, and the EVA suit battery life. The onboard rover navigation mode, which is currently displayed, displays a digital wayfinder with direction and distance to the lander, EVA suit battery life, and the Explorer battery life. All right, that's it. I don't know if...
That was good.
all right.
Navigation is critical in Explorer's ability to operate robotically during the autonomous and end-of-life phases of the mission. Explorer will use stereo cameras and an inertial measurement unit to perform visual inertial simultaneous localization and mapping, or VSLAM. Explorer will also use a long-range stereo camera and a flash LiDAR system for surveillance and obstacle avoidance. We propose the following sensor layout to partially encompass the stereo camera's field of view within the lighted region of the headlights in order to optimize the performance of the VSLAM algorithm. This is because we can calibrate the algorithm to suit the headlight conditions, which are constant, rather than the varying illumination conditions of the lunar surface. To test some of these theories, we did some experiments. The first experiment uses the PID controller to show control response of the yaw control. The experiment demonstrates the Segway's ability to autonomously yaw at various desired yaw angles on a smooth, flat surface. From our results, we can see that the performing yaw maneuvers with skid steering yields decent results as the IMU forms a semicircle arc trajectory. The ideal scenario would be to generate a perfect semicircle arc trajectory, since the IMU is mounted at a fixed distance from the Segway's center of rotation, and the yaw rotation should occur about this point. The results also show that over time, the Segway experiences estimation bias as it performs stationary yaw. This is evident through the generated offset between the initial location and the final location of the IMU estimation. The offset generated suggests the slippage of the wheels occurred during the yawing motion. We were also able to use April tag detection to develop vision-based tracking via the yaw control. To achieve this, we used an Xbox 360 Kinect stereo camera to determine whether the April tag is detected in the Segway's field of view. If the April tag is detected, determine the pose of the April tag, and determine the yaw angle error between the desired yaw angle of the April tag and the current yaw of the Segway. The yaw error is then used to implement a pre-existing yaw controller, where the feedback control allows the Segway to track the April tag. In addition to the Segway, the Explorer team had planned to implement the autonomous software to Raven. Prototyping development of Explorer shifted from the Segway to Raven platform because it can support the autonomous and crewed capabilities that are required for the Explorer design. Raven was previously controlled by an Arduino microcontroller that converted signal from a joystick input into a PWM signal to actuate the motors. Jaguar motor controllers are used to power the motors from the microcontroller signals. In order to allow for autonomous capability, we determined that a Raspberry Pi would be a suitable host for motor actuation. The Raspberry Pi required configuration to allow it to supply logic signals to the motor drivers. We then determined the duty cycle of the motors and were able to successfully drive the motors at varying speeds, as shown in this video. Due to the COVID-19 pandemic, we were unable to complete the full implementation of autonomous control.